Everybody. Hope you're more morning people than I am. I've had about 25 cups of coffee though, so I should be good. And if I vibrate, that's why. As Tom mentioned, I'm a USDA ARS scientist. I'm a soil scientist specifically by training. We're in Beltsville, just outside the Beltway in that Washington, D.C. area. And Tom asked me to come back. Last time I was here was in 2006, hence the update. So, every decade or so, maybe I'll come back. Which is actually, part of the story here is that we're doing long-term research. And the reason that we're doing long-term research is multiple reasons for doing that. And I'll get to that in a second. And I have in the title long-term organic farming research, but we also are looking at conventional systems. So we'll do some comparisons and there'll be questions to look at on both those. There we go. Okay, so why do we do long-term research? We are now in our 23rd year of essentially doing the same thing on the same piece of land. Well, that's what farmers are doing anyway, right? So what we're trying to do is we're mimicking what farmers do in the mid-Atlantic area. And this is the only way when you do long-term research to do a couple things. To measure things that change very slowly, like soil carbon. The longest running LTAR, long-term agroecological research site in the world, is in England, and they started in about 1859, and they're still seeing changes in soil carbon in some of their systems after that many years. It happens slowly after that many years, but still something to look at. There's a lot of things that change from year to year a lot. As you all know, crop yields change from year to year. Other environmental aspects like nitrous oxide emissions also change dramatically from year to year, and these are largely based on changes in weather from year to year. And these long-term type studies are the only way, or the best way, to provide robust data for crop modelers that can look at things in the long term. So specifically, the Farming Systems Project, which is what you see in the photo here, was established in 1996. And it's one of 5 US LTAR's long-term agroecological research sites that includes both a no-till, a conventional no-till, and some organic systems. So we're looking at fairly different management regimes, but it's the only one that has both no-till and 3 different organic treatments. So we do focus a little more on the organic. We have a unique site to do that. That's why the organic's in the title. And as I mentioned, we're trying to mimic mid-Atlantic farms. And so we work closely with both extension, especially for our conventional systems, and then with organic farmers for organic systems to make sure that what we're doing mimics what farmers are doing. So these are our 5 systems. We have 2 conventional systems, a no-till and a chisel-till, and then we have 3 organic systems. And you'll notice in all our systems we have corn followed by a rye cover crop, and then a full season soybean in all 5 systems. In our conventional systems, we come in with a winter wheat and then a double crop soybean. So these are our conventional systems, 4 crops, 3 years. And you'll notice in our organic system, we have a similar type of rotation here where 3 crops in 3 years, and then in place of this soybean, double crop soybean, we come in with a vetch rye cover crop, and that's because we need to provide the nitrogen for our coming before corn here, which is a high nitrogen feeder. We also have a 2-year rotation, very short, corn with a rye cover crop, soybean, and then we try to get our vetch and rye mixture in, again, to provide the nitrogen for the corn. And then we have a 6-year rotation, corn, rye, soybean, wheat, and then 3 years of alfalfa. So quite different range of crop rotations, and so we can test effects of crop rotation length among these 3 on sustainability. We're looking at all kinds of measures of sustainability. We're looking at crop yields, we're looking at economic performance, we're looking at environmental performance, we're looking at soil health, all kinds of things that we can do in these long-term systems. So we have that comparison. Then we also have another comparison, as I kind of implied before, the two conventional systems that are a 3-year rotation and the organic system that's a 3-year rotation. Similar rotations with this small difference here in the type of legume that we have. So I mentioned that one of the things that these long-term sites are good for is to look at things that change a lot from year to year. It's a non-irrigated site. I don't know if you've looked at these type of data. This is corn grain yield in our 5 systems. And so a number of my slides, I'll have this color scheme with the conventional tilled conventional system, the no-till conventional system, and then the 3 organic systems with these kind of more green colors compared to the brown. So what do you see here? You see a couple things. One, huge amount of variability from year to year, right? Even in our best systems, our conventional systems, we're essentially going from 20 bushels in our worst year, 27 was a very dry year, to about 200 bushels in our best years, which is not bad for this site. We're on silt loam soils, we're on coastal plain soils, just this side of the fall line. So not the sandy soils that you find in some parts of Maryland here, but still these types of soils are found on the eastern shore as well. So you see this huge variability from year to year, and you can see just from this, you know, if you did a study in 2004, 2005, you probably have quite different results than if you did 2006, 2007, right? So that's one of the values of this long-term research. And there's more variability from year to year than there is among the different cropping systems in a given year, showing the huge impact of weather on these types of data. And we did a more careful analysis of relating this to weather. And when we do that, we see that rainfall 6 to 10 weeks after planting, and this is for the organic systems because we have different planting dates for organic and conventional. This largely explains this. And you can see when rainfall is high, during this very short time period, right? That's just 5 weeks during the summer, during late vegetative and early reproductive stages. You can have wonderful weather the rest of the year, things can look great, but those 5 weeks either give you this or they give you that. So this type of analysis is pretty interesting. When we did this, we submitted it for publication like scientists do, and we got back a response that said, you only have 18 years of data. And we're like, what? It's 18 years of data. And they said, well, for this type of analysis, you really need 30 years of data. So that also points to the importance of even longer data set term data to record this type of variability over time. Since then, though, I've spoken with some weather people, climatologists, who are talking about how climate is no longer stable and it's changing so fast that maybe we should work on a 15-year time scale for these types of analyses. And I was like, oh, well, I should have talked to you before you got these reviews back. But to be fair, the 30-year issue is more of a statistical issue. But the changing climate does play a little bit of havoc with that kind of thinking. Soybean yields followed a similar pattern, but not quite as high up and down as you might expect. Soybeans are a little more forgiving, and our wheat yields are a little more stable. I don't have graphs to show you that, but let's let you know that. So let's look, but we can still look at the differences in these management systems, you know, in any given year. And what I'm doing here is showing you what we're calling good years, which is basically when we had, during that critical time period, we had about 20 centimeters, so that's about 5 inches. Is that 5 inches? 20 centimeters, you guys do the math. 4 inches of rain during that critical time period. So we're looking not at the effect of drought anymore, we're looking at the effect of the actual cropping system. That's the basic point. And so you can see, so these are the average. You can see that in our conventional systems, we're at 140 bushels per acre on average. And you see in our 3 organic systems, not only are we have lower yields, but that there's this stair-step pattern here. We're in our short rotation, we're down at about 6 times 16, whatever that is. Sorry, I didn't put these in bushels per acre. I forgot to do that conversion before coming out here. So I'm doing it on the fly here. 6 times 16, 60, 96, thank you. So this is about 100 bushels. This is about 110, I think. This is about 125. So anyway, to give you an idea. So we get these differences. Why do we get these differences? One thing we're able to do in these long, skinny plots that you saw in the original photo is we can put in a lot of microplots. So what we can do, and we've done a lot of this, is we take a little area and we hand weed whatever weeds have survived the cultivation and the rotary hoeing and whatever is required in the organic systems, and whatever might survive through the no-till herbicides, which we usually don't get very much. We hand weed that, And so then we have a small area where we've taken all the weeds out right next to an area which has whatever weeds survived the mechanical cultivation. And then we can look at the difference in crop yield in those two different plots and ascribe the amount of yield decrease that's due to weed cover, right? So in those microplots, this gives you the percent cover of weeds for 6 years, 2-year rotation, 3-year rotation, 6-year rotation. You see quite a dramatic effect of that rotation length on the weed populations. And why is that? In this system, org 2, we have corn 1 year, we have soybeans another year. A good year for corn generally is a good year for soybeans, and your time of killing weeds is generally the same time of year. So a weed that escapes during your corn phase is going to be a weed that also is a problem in your soybean phase. Once you put in a winter wheat crop, now you've broken that weed cycle. Those weeds that are germinating in the spring, they're going to be outcompeted by the wheat. Even if they do survive, which they generally don't, we come out and kill them before they're flowering and going to seed. So that's a huge difference. And then kind of similar concept when we throw alfalfa into the rotation. Now we're cutting 4 to 5 times a year. Those weeds not only don't have much chance to survive, but turns out we start getting different types of weeds. We start getting more grasses than we do the broadleaves. And that percent cover has a direct impact on actual corn yield loss to weed competition. So this means that we lost about 35% of our potential yield in this, when we had a lot of weeds in this short rotation, and we lost about 14% of that yield loss, of that yield. So pretty straightforward, but that whole concept of these microplots is something we've taken advantage of in a lot of the data I'm going to be showing you. In terms of soybean grain yield, similar type story, except now our soybean yields are more similar to our our organic soybean yields are more similar to our conventional yields. Now we're multiplying by 15, so that's about 45 bushels per acre. And I'll let you guys do the math right there, because I can't talk and do math at the same time. But you see the effect. And we did some of those microplots in those systems, and here's a photo showing one of the very weedy years. You can see here, this is one of those microplots where we hand weeded. And from this, we learned that all the yield loss in the soybeans was due to the weeds. One point I forgot to mention for the corn is that yield loss did not explain all the difference between the organic and the conventional, and I'll get back to that in just a little while. And so then we can develop some equations where we looked at every 1% increase in weed cover results, and here I did do the conversion for you, results in 2.6 bushels per acre yield decrease. So it's weeds are pretty effective at reducing soybean yield, and that's because we're getting some shading and we're getting competition for moisture as well as nutrients. Probably more moisture than nutrients for soybeans. And this, as I mentioned, this explained all the yield differences between the conventional and the organic. So weed control in soybeans, and I'm sure organic farmers will tell you that's kind of a story they've seen as well. In terms of wheat grain yields, we're not seeing very big differences here. Historically, what we did for managing the nutrients in the wheat is we would apply 2 tons of poultry litter. I forgot to mention, poultry litter is used in all the organic systems, but none of the conventional systems. That becomes important a little later. So to get these yields, we would incorporate 2 tons of poultry litter in the fall, and we'd get pretty decent yields of wheat. That mineralization of that manure, even though it's not really supposed to happen in those colder months for wheat, I think we're still getting some. And so we are getting sufficient nitrogen, I think, by managing our wheat that way. Having said that, we can't do that anymore because of the nutrient management changes, where we can't apply that much nitrogen or phosphorus in the fall. So we do the fall soil nitrogen test to determine how much fall nitrogen we can put on. And it looks like, and I haven't compiled this yet, it looks like our yields might be coming down because what we're doing now is applying the poultry litter as a spring application at green up, the way you might in a conventional system with the synthetic fertilizer, which is what we actually do in our synthetic systems. So stay tuned. In a decade, I'll show you what that looks like. So one thing we looked at, this coming back to the corn and the fact that we couldn't explain all the difference between the organic and the conventional yield. One thing we've heard from farmers and others is that maybe the varieties that are available for the organic farmers are just not as, there's just not as much choice because we don't have the critical mass. And so maybe there's a yield drag in the organic varieties just from that reduced diversity of options. A lot of those varieties were developed in the Midwest, not necessarily for our region. None of this do we know for sure, but what we can do is we can plant the two varieties, the organic variety next to the conventional variety, in the same field and manage it the same way. So what we did is we did exactly that. We planted the organic next to the conventional variety. We managed it all using no-till because we know that's easier to manage. And then we did it at two different planting dates because the conventional we plant earlier than the organic. So we have what's called a 2x2 experiment, two different varieties, two different planting dates, and then just looking at the yields of those varieties. Now this is not a comparison of all organic varieties and all conventional varieties, but it's a comparison of the varieties that we use in this experiment. So it's kind of a little bit of on-farm research in a sense that, that you could do as well. That's what all that says up there. This is just a photo of the two varieties next to each other coming the end of the season. And hopefully you can see this from the back of the room. This graph then shows some of the results from the early years. I haven't compiled the later years of this experiment, but what these numbers are here is the grain yield of the organic corn variety as a percent of the conventional corn variety. So if this number is 100, that means they yielded the same. If it's less than 100, the organic yielded less than the conventional. And I just put up a couple of years here to show the variability. One year was a normal year in terms of rainfall. One year was dry, one year was very dry, and one year was, again, normal. We didn't do this comparison that year for various reasons. I think the planting date was actually the same for conventional and organic that year. But the point is, if you look at all these numbers, they're all below 100. Some of them are very close to 100. So some years we're not seeing too much of a yield drag. But overall, when we look at the mean, we get about 86% of the yield from our organic varieties than we do from our conventional varieties. So this suggests a 14% yield decrease just based on variety selection. And that variety selection is made based on consulting with seed companies and seed dealers and whatnot. So again, it's not an overall comparison of organic versus conventional varieties, but it is specific to this experiment. So that might explain some of the differences we see in our corn yield. I should just point out, we've also, something I won't necessarily show you right now, but you can see here we have some microplots there where we use nodulating and non-nodulating soybeans to estimate soybean nitrogen fixation. I'm not going to talk about that today because we haven't summarized those data, but if you have questions on that type of thing, I can talk about that more later as well. So we also look at net economic returns. This is for some of the early years of the study. We've just updated this recently, and I'll talk a little bit about that, but I haven't prepared a graph for you, but the results are somewhat similar. So dollars per acre, we got our 5 systems. The brown bars here are the returns without an organic premium. Just for comparison purposes, obviously in the conventional systems, that's the only option. You take your seed down to the elevator, you ask them what they're paying you, and that's what you get. No organic farmers I know of get this brown price. They get the green price, right? They get the organic price premium. So we're seeing much higher returns, but there's one more number on here I want to show you. That's the standard deviation that's above each board. That's the amount of variability from year to year. In our conventional systems, we have relatively low values here, but in our 2-year rotation, 381. That number is higher than our mean. So that's basically saying 1 year you're getting, it comes back to the concept, a good year for corn is a good year for soybeans. So some years you're making a lot, some years you're not making much, if any. So this is the same story as the increasing your rotational crop diversity helps stabilize things. The same story as we saw with the weed, right? So you're not putting all your eggs in this summer annual basket of corn and soybeans. You add wheat, you reduce that variability. You add alfalfa, you reduce it even more. And it turns out that alfalfa returns can be reasonable. We actually did not charge an organic price premium for our alfalfa because that whole market is very complicated. We didn't think our alfalfa was of sufficient quality for that market, so it was a lower quality. We just took kind of a lower quality price for that. Overall means not different, but the variability quite different. And so that's something to pay attention to. I mentioned that we updated these data. That paper is in review right now, which is part of why I didn't want to present it until we get the full feedback from the outside reviewers. But in essence, we're seeing that these shorter rotations are not performing quite as well relative to the longer rotation. We're seeing our best results in this longer rotation. And that's going from, this is up to 2005, so this next analysis from 2006 to 2014. So a good number of years there. All these data are based on the price of inputs and the price of grain and your yield as well. Our yield patterns are still similar, but the price of inputs, especially in 2007, 2008, changed quite a bit. The grain prices, organic versus conventional, have changed. And so we can update this, and next year I could give you a better update on that, a more complete update. But essentially, we're still seeing the stability and the higher returns for the longer system, but less so for the shorter systems. So stay tuned for more on that. Okay, so that's production and economics. Let's talk about soil health and environmental issues. As I mentioned, measuring soil organic carbon changes is one of the things you have to do in the long term. This changes slowly. These are data actually collected in 2006. We've also collected in 2011 and 2016, and we're seeing similar type patterns. But these are the data I've worked up the most. And there's a lot of long-term experiments where you have a conventional till and a no-till system right next to each other. And a lot of those data show that you get more carbon in a no-till situation than in a conventional till. Not in organic systems, but just in conventional systems. We don't really see that in this system. I'm not showing you the conventional till, but it's about the same here between these two. And when I first did this, I said, well, what do I expect? Scientists, we have to come up with a hypothesis, an educated guess on what we expect to happen with a reason why that is the expected response. Since there's a lot of data on no-till and chisel-till, my hypothesis there was that we'd have more carbon in our no-till than our chisel-till. Chisel-till, conventional till, I use them interchangeably. Sorry about that. But because tillage tends to increase the decomposition rate of carbon. So I thought, okay, that's an easy hypothesis. There's a lot of data for that. I was wrong. No real differences. I think that has to do with the relatively warm, humid climate we're in. But that's all I'm going to say about that. What I didn't really know and have a basis for coming up with a hypothesis was where our organic systems would fit in, because there's just not long-term data sets for that. So we don't have a good sense of that. There are some studies for sure around the world, but at the time that we were doing this, there were not as many of them. So I predicted, well, we might have more carbon inputs in these organic systems because we have the poultry litter, we have the cover crops, but we're doing a lot more tillage, and we know that tillage is going to reduce our carbon, so what should I do? Well, I'm going to guess that the 3-year organic, which has similar rotation here, is going to have less carbon overall than no-till. And look what I found. I'm wrong. So this is a good way to learn. If you're wrong, you learn something new, right? Why is the carbon higher in the organic 3-year than in the no-till? One thing I learned since I made that hypothesis is that our carbon inputs in all our 5 systems looks to be about the same. So that kind of even makes this finding even more challenging. We have the same amount of carbon inputs, but we have a lot more tillage here. We obviously have no tillage here. We have a lot more tillage. Those two things together should lead you to think that this carbon here is at least going to be, it might be the same here, but it's more likely to be lower. How could it be that is this challenging basic soil science principles? Not necessarily. Where does most of the carbon fall? Well, let me step back 1 minute. Why do we have the same amount of carbon in these systems? I told you we have more poultry litter and cover crops here, but in the no-till system, because we have higher corn yield and soybean yield, we have more residue returned to the soil. So our carbon inputs are about the same because of that, But in the no-till system, we're depositing all that carbon, pretty much all of it, on the surface of the soil. That's where the bulk of the above-ground residue falls. There's much more above than below-ground residue in these annual systems. And so if we then look more closely at the carbon, so this is down to 1 meter depth, right, about 39 inches. We took soil cores, this is the same data presented in a different way. We took soil cores from 0 to 1 inch, 1 to 2 inches, 2 to 4 inches, 4 to 10 inches, and then down below here where there's no real differences. And you'll see that my hypothesis was correct in the top 2 inches. We have more carbon in the no-till, we have less carbon in the chisel till or conventional till, and organic is right in between. Hey, I was right, kind of. But look at this, in these organic systems, this is where we're putting the carbon, right? We're using a moldboard plow, we're using a chisel plow. We're putting the carbon down below. At that depth, we have more clays, and we have probably less oxygen, so slower decomposition rate of that carbon at that depth. So it's accumulating at that depth. And this has implications for climate change and for soil carbon sequestration, which we can talk about later, but that's not what I'm going to focus on here. As a farmer who is not getting paid for your carbon sequestration, why do you care? Is this going to be interesting? Is this going to be valuable in some way? Let me just go back real quickly. What I should have put up here, let me see, let me put it this way. If those bores included the carbon all the way down to this depth, if we focused on the carbon at these depths here, the total organic matter between our conventional and our organic systems is not that different. It's for a typical soil fertility sample depth of about 6 inches or 8 inches, 6 to 8 inches. Soil carbon in our organic systems is about 1.6%, in our conventional systems about 1.4%. As a agricultural professional advising farmers, would you take that number and say you're going to get a big yield bump? Who would do that? Who would tell you, who would say you got 0.2% increase in organic matter, that's going to give you some economic benefit? Nobody, right? Did any of you go to the nitrogen credit talk by Doug Beagle or any of Tom Morris's talks on nitrogen, yield goals and all that? This next slide is what I've been thinking about in that context. Let's just go to it. Oh, just a reminder, we're doing a lot of tillage in the organic. This is, okay, not this one, sorry, 2 slides from there. This is the prelude to the next slide. John Spoiger was a postdoc in this project with me for a while, and he looked at potentially mineralizable nitrogen in these 5 systems. This is just a graph of of the results from taking your soil into the lab and doing a mineralization study and seeing how much nitrogen is released from that soil. You notice our 3 organic systems are above the 2 conventional systems, and then you can do some math and find out how much potentially mineralizable nitrogen there is. And if you look at these little B's after these numbers here versus these A's, this just tells you that the amount of nitrogen released is quite a bit higher in these organic systems compared to these conventional systems. So now, who cares? What difference does that make in terms of corn yield? So John set up some microplots where one year in 2009, we applied no nitrogen in the corn phase of the rotation. So no legume cover crops, no poultry litter in the organic system, no nitrogen fertilizer in the conventional system. What do you expect based on that 0.2% change in organic matter? Look at that. And we irrigated and we kept these all weed-free. So this is a measure then of how our previous management affects corn yield based on nitrogen release. So it's a in-field test of the value of that nitrogen mineralization where we took the soil into the lab. So 160 bushels per acre about for our organic systems, no nitrogen added. About 110 bushels in our conventional systems, no nitrogen added. So here's a case where about a 0.2 difference in organic matter gave us 40 to 50 bushels of corn. This kind of is a reflection of why that nitrogen, that whole nitrogen cycle and yield goal predictions are very challenging. This is way beyond expectations. Granted, this is one site, 1 year, but it is relevant for this site, and it is relevant to help us understand what our systems look like here. This tells me we're not nitrogen limited in our organic systems. In our early years we were, but this tells me if I can grow 50 to 60 bushels of corn by adding no nitrogen, I think adding some legumes and some poultry litter, we'll get plenty of nitrogen, right? Unfortunately, there's some downsides to having essentially what I'm using this slide to tell you that we probably have too much nitrogen in these organic systems. This is nitrous oxide emissions. Nitrous oxide is a greenhouse gas. If you're here for the last session where Lou Ziska talked mostly about CO2. CO2 is the important greenhouse gas, but nitrous oxide is also one of the two others, the methane and N2O. Agricultural systems are the primary source of nitrous oxide, and you can see from here, it doesn't matter what your nitrogen source is, it matters how your systems are managed, how much N2O you're gonna release. Because we have so much nitrogen and so much N mineralization in these three systems, turns out the difference here between the 2-year rotation and the 3-year conventional systems, we actually get most of this N2O during the soybean phase of the rotation. We're not adding new nitrogen, but those reserves of soil nitrogen, there's plenty of nitrogen around. The soybeans, they can fix nitrogen if they want. They can take it up from the soil, which is probably what they're doing before they're fixing, but there's still residual nitrogen, and we're getting this N2O. Same in the 3-year rotation. After we harvest our wheat, or before we harvest our wheat, it's senescing, so there's no nitrogen uptake. If the soils get wet, N2O is produced when the soils get wet and you have too much nitrogen, is one way to think about it. We have a period here in the 3rd year, in the wheat phase of the rotation, where we also can get a lot of N2O because we don't have crop uptake. If we have wet period during then, we can get a lot of N2O. Once we throw in alfalfa, during the alfalfa phase of the rotation, we're not getting a lot of N2O. So that kind of dilutes out the effect of those other portions of the crop rotation. When I first started doing this type of study, I focused on just the corn phase of the rotation because that's when we're applying most of the nitrogen. That's when I thought we'd get the N2O. But you need to look at the whole crop rotation. You need to look year long to get these type of assessments. It's probably more about N2O than you ever thought about, but it is something to think about in terms of the impact of our management systems. Kind of an associated point, I don't know how well this shows up, soil test phosphorus. This is in 2015. Because we're adding more poultry litter in these two systems, I forgot to make that point earlier, but we're adding the poultry litter every other year for the corn here. And here, two of 3 years, once in the corn and once in the wheat, we are adding more poultry litter over time than we are in our 6-year rotation. And I have a postdoc who's updating a phosphorus balance right now, showing that in our long rotation, we're pretty much balanced in terms of our phosphorus inputs and outputs as we are in our conventional systems. But in our shorter systems, we have an excess of phosphorus that we're applying, even though we're applying the poultry litter on trying to do like a phosphorus replacement basis in looking at how our cover crops are performing and increasing the nitrogen based on cover crop performance. So we are being conservative, but our phosphorus is still higher. We're not at a level to be too worried about yet, but it just shows the general principle. I think we might be okay, but we need to look at that a little closer on how this has changed over time. We had another graduate student. We work closely with the University of Maryland, which is just 4 miles down the road. So some graduate students sometimes interested in looking at the data that we collect here and summarizing it. Here's a study by Eric Hoffman, where he took all our input data. You know, we keep records of everything we do, all our management, operations, inputs, and all that, so that we can calculate how much energy is used to produce the crops. So this is energy, and I don't have the key to show what the different colors mean, but these are the different crops in the rotation. So let's just focus on the very total amount of energy used here. We're using more energy in our conventional systems than in our organic systems on an area basis. What's that because of? This black is the corn, and that reflects the cost of nitrogen fertilizer. Nitrogen fertilizer is very energy intensive to make. This is per area basis, this is per yield basis. Since our yields are lower in these two organic systems than in these systems, now our energy per unit of production is getting higher. So you really need to look at how you look at these things. But again, our 6-year rotation is looking better in terms of energy inputs into the system. Just another measure of sustainability. Soil loss, of course, another measure. I apologize for the units here. Frankly, I don't know how important the units are because here we're using WEP, here we're using Russell 2. These are models, and really it's the relative differences that we want to look at, maybe not the absolute. If we look at our three-year rotations, as you might expect, no-till is showing the least amount of soil erosion, and the conventional till is showing the most. The 3-year organic now is in between those two, and that has largely to do with the fact that we have more cover crops. So over the winter time, we're protecting the soil from erosion, the original meaning of the term cover crop, to cover the soil. Then we used Russell 2, and we just looked at our 2, 3, and 6-year organic rotations. Maybe not too surprising, but when we have a perennial forage in the system for 3 years, that's the best way to reduce our soil erosion levels there. Don't compare these numbers to these numbers, though, because we're using different models here. We have not done the analysis using the same model in all systems, but we're looking to do WEP on all 5 systems this coming winter. So again, next year, I'll be back, maybe. So in conclusion, among our organic systems, longer, more complex rotations have greater corn yields, less economic risk, lower weed pressure, equivalent soil nitrogen availability with lower dependence on manure and therefore potential phosphorus loading, lower N2O emissions, lower energy use, and reduced soil erosion. Just a summary of the graphs I've shown you. If we look at all 5 systems, we're seeing multiple trade-offs. If we just look at conventional versus organic, I showed you crop yields. Conventional yields are higher than organic, but the net returns are higher in organic than conventional, with the caveat that our most recent analysis makes this maybe a little more complicated, that the longer rotation might look better than the shorter rotations. Soil carbon, more in the organic than the conventional, and that has some soil fertility impacts, like I showed you. In terms of soil erosion, comparing our 3 systems, no-till less than conventional till with organic in the middle. Obviously, fertilizer and herbicide use, we don't use them in organic, so well, we use some fertilizers in organic, I should say, but no nitrogen fertilizer and no acid-based phosphorus fertilizers. The energy use was a little more complicated. And greenhouse gas emissions, again, more complicated. Not just a conventional versus organic, but it really matters how you manage your organic systems. And this is a role for conventional systems as well. If we want to reduce some of these impacts, we have to look at specifics of how we manage, whether it's organic or conventional. There's no magic bullet. There's no organics are going to be better than conventional for this, that, and the other all the time. You really need to look at the details. That's where the devil is. So that's what we're trying to do with this long-term study. And final conclusions that the trade-offs are common when you're comparing any agricultural management system. Organic systems could be improved. Conventional systems could be improved. So what we really need to do is look at new methods and technologies to improve both of these. So a whole nother talk that I could give along with my colleague Stephen Mirsky is reducing tillage in the organic systems. How can we do that? And then also incorporating more cover crops in the conventional systems and maybe including some poultry litter in the conventional systems. So there's a lot of tweaks that we could change to improve these systems. And in addition to these long-term studies, we also do some short-term studies at Beltsville, kind of focusing on that. How can we improve these systems? That's all I've got for you. Thanks a lot. Appreciate it.
So you have a few minutes for questions, if you have any. Yes.
Yes.
So if all organic farmers go to the 6-year crop rotation, have 3 years of alfalfa, it's not going to bottom out the alfalfa market?
Yeah, so the question is, if all organic farmers go to the 6-year rotation and they're all doing alfalfa, isn't that going to bottom out the alfalfa market? Yeah, good question. And there's other issues there. That's probably not going to happen. Not everybody's going to do it for other reasons as well. And that's why I would point you to some of our other research where we're looking to reduce the tillage in the organic systems. There's an organic farmer, Steve, I'm gonna put you on the spot. There's some organic farmers that are using some of the lower till methods in organic, and Steve was sharing a lot with me his specific management details where, and I hope I tell this accurately, Steve, but where they'll do a zone tillage, right in the row, they'll plant in there, and they'll use some flame weeding to control weeds in the row. And so between the row, you still have your cover crop in there. That's going to help with all your soil erosion. So then they can grow bigger cover crops, and then when they come back and use some weed control, hopefully better weed control as well. So this is not, I'm not saying this is not the only way to improve the sustainability of organic systems. It's one way. Having said that, some of the longer term organic farmers in Maryland are using the 6-year rotation, and they've been using it for a while, and they found that that was the best way for them to manage things. But that was before we really started talking about kind of this reduced till organic rotations, where we're still tilling some at some portion of the rotation, especially to establish a good cover crop, or at whatever phase makes sense in your rotation. But there's definitely new tools now, with all the GPS guidance and all that. That's really helpful for the organic guys. And we've started using it in these systems too, so that our weed control is actually improved, just based on that. So this is one example, there's certainly other ways. And the organic, each individual organic farmer needs to make the decision that works for them, et cetera, of course.
So you're doing cultivation by GPS?
Yeah, we have, so our tractor is, GPS driven. So some of the farm crew members that do all the work out there are here at this meeting. And so I could, if they were here, I'd ask them to help explain that, but they can do hands-free driving for the cultivation. For the cultivation, they're still paying pretty close attention, but they can look behind them a little easier than they used to be able to. All the planting is done with GPS, and that helps a lot because, we have 12 rows here, and we have 4 and 6 row planters, so getting those 2 edge rows from that one pass exactly lined up, that helps a lot, when you're coming back to cultivate between those rows. So there's a couple things, that help a lot. And so that's kind of made me a little bit of a convert on some of this, high-tech stuff. In addition, I don't know if any of you were at the, was it Tom Morris that spoke about doing on-farm trials where he was talking specifically about nitrogen fertility response. But because of all this automated tractor equipment, farmers can do their own on-farm research much more easily than they used to be able to. And with these microplots, that's kind of what we're doing, is if we treat each of these, if we consider this a farm, if this is our 6-year rotation here, this is the corn, soybean, this is the alfalfa, and there's a couple of others, anyway, this is our 6-year rotation here. Essentially, that's a small farm, and these microplots are kind of that same concept. We can do it by hand because it's a smaller scale, but with this new technology, people can do their own research on their farm to understand their farm, not to understand the means that are developed across the state by looking at 5, 6 research stations, the traditional. I guess that's the most exciting thing I found at this conference. That's why I'm sharing that. I think there's a whole new world out there for improving all these systems, because farmers and consultants can now work together to better understand an individual, not try to make recommendations based just on these means, which have a very wide variability. That was a very long-winded answer to a question you didn't ask, but I thought I'd share that as something I thought was kind of cool. Any other questions, thoughts, concerns, jokes?
I assume you maintain pH?
Yeah, so we use lime, and we have high magnesium soil, so we try to use high calcium. We have the farm crews out here. We have farm crews that are very good at staying on top of things. I depend on them a lot, you know, with some of that stuff. Some of the things that we need to apply, we use potassium sulfate, that's, you know, within the organic systems that you're allowed to use. They'll use potassium chloride sometimes, you know, muriate of potash versus OO50. And so sometimes we have to do you know, we have to have special stuff for some of our treatments, but for other ones, we depend on their best management, for the conventional systems especially. And they've learned a lot, they've contributed a lot for this whole organic management as well. I'm a soil scientist by training. I'm not an agronomist, but I've become an agronomist just by learning from them. So it's kind of neat. And by learning from organic. Are you an organic farmer yourself?
No.
Okay. Yeah. So, but also learning from the organic farmers. We have an annual workshop in Queen Anne's County organized by Jenny Rhodes, and she brings in people. We have about 60 to 100 people every year where we discuss in more detail some of these management issues in organic, and sometimes at farmer panels, and that can be very helpful to get a sense of, you know, keeping up. Things keep changing all the time. I was telling Steve last night, I thought it's a challenging time to be a farmer, but it's also probably most exciting time because of some of these technology opportunities.